Okay, welcome to the third and last item of the MathSAPS 3, which is Graphs and Networks, Chapter 6 from your textbook. And by the way, this is 65% of the assessment item at the end of the semester that you're going to be sitting, and that is the 45% test. So, Chapter 6, Graphs and Networks. You've met graphs before in Year 11, and networks. Remember matrices? And we start with 6a, Graph Theory Basics, solving what is called the Königsberg Bridge problem, but solving it in terms of vertices and edges of networks, which we will then explain as we go through. So here is a map of the city of Königsberg as it was in 1651, and so you can see it's a very old drawing. There are a few houses. There is, if you can make it out, a river system, and even more difficult perhaps to make out is that there are bridges over the river. So on the next slide I will make those particular features clear. So here we go. This is a part of the river system. And a bit more. There we go. And then there are bridges. And there are 7 bridges altogether, which we will colour in next. 1, 2, 3, 4, 5, 6, 7. There we go. And the good citizens of Königsberg used to spend Sunday afternoons seeing if they could take a walk that involved crossing each bridge once only, starting anywhere and finishing anywhere. And they tried this and they couldn't prove that they could do it, and they couldn't prove that it was impossible either. This was the problem that plagued the citizens of Königsberg, which by the way is in Germany, at least it was in Germany, and now it's in Russia and has a different name. So, could you spend Sunday afternoon crossing each river bridge once only? Those are the 1, 2, 3, 4, 5, 6, 7 bridges, and here again is the river system. Nice blue water. Along came a mathematician called Euler who lived in that city, and he said, we're looking at the problem in the wrong way. We mustn't be looking at the river and the bridges, we must be looking at the land masses. And if you look at this picture here, there are 1, 2, 3, 4 land masses. One above the river system, one enclosed in the middle, an area to the right, and an area below. And what he suggested is that you make a stylized drawing like this. So here's the 7 bridges in the river system, same as before. What you should do is mark the 4 areas, 1, 2, 3, and 4. Like this. So you identify the vertices with 4 blobs like that, and then draw a line from each blob to every other blob using whatever bridges are available. Here we go. First one, second one. These are going to be called the edges of the network. The pink blobs are the vertices and the black lines are the edges, and there's got to be 1 for each way to join up 2 blobs. This is the same diagram out of the textbook with the 4 vertices labelled A, B, C and D. And what you do next is make a stylized version of it. This is what Euler did, so you should be able to see it's the same diagram. It's just that we have nice neat circles and nice straight lines, and this is what a graph normally looks like. See, it's the same diagram. Yep, Euler's diagram. Euler is E-U-L-E-R, by the way. Next thing I'd like you to do is identify what we call the degree of a vertex. Now A has got 1, 2, 3, 4, 5 arms coming off it, B has got 1, 2, 3 coming off it, C has 3, and D also has 3. So they're all odd vertices. We'll just put what we call the degree of the vertex next to it. And what Euler said, and I'm not going into the deep mathematics here, but he said that if a network has got more than two odd vertices, or odd nodes they're sometimes referred to, then the network is not traceable. In other words, you cannot run your pencil over the whole network without lifting your pencil from the paper. Now let's try tracing it. And BC has been omitted, so try starting somewhere else. And again, this time CD is not covered. So what do we do about that? Well, probably build another bridge. If we build a bridge from B to C, then B has now got 4, C has now got 4, and A and D are still 3. The question now is this traceable? So we'll just get rid of those numbers and put the line back in again. Change the numbers. We have two odd nodes. Now, Euler said this is traceable, but in fact it's not always traceable. It rather depends on where you start. So what you should be doing in your books is making a copy of this diagram and then trying to trace it, starting at various places until we can establish where you can start and where you can't start. You're starting at D. Yes, we've managed it. So remember that, starting at D, we can trace it. Clear that off. Try starting at B. No, we're missing A to D on the right hand side of that circle. So yes, we could start at D, but no, we could start at B. Why in one place can we start and why can't we? Let's try starting at A. Indeed we can. So we can start at A and D, but not B. And it turns out that you can trace this network if you start at one of the odd nodes, but not if you start at one of the even nodes. Not only that, if you start at one of the odd nodes, you will always finish up at the other odd node, and that is what Euler discovered. And that concludes exercise 6A introduction, with the work to be done on page 202.